Hi, Math A Honors students. This is Mrs. Dangle again. I hope you're having a wonderful morning, afternoon, or evening. Thank you so much for joining me. I'm going to be covering 7.2D lesson, Growing and Shrinking Objects. So go ahead and get out your printed copies, or you're editing on a PDF, or you can handwrite this on a piece of paper. Just follow along with all of the work that I show here and number it accordingly. Okay, I've already began a little bit on number 1, because I wanted to look at the ratio of my side lengths of these figures below. So in problem number 1, it says, are the two figures below similar? If so, state the scale factor. So two figures that are similar have the same shape. So we are looking at two rectangular prisms here. So they do have similar shapes. Then we also want to look at the ratios of their corresponding side lengths and find out if those ratios are equal. So corresponding side lengths are where two side lengths are in the same position but on different figures. So 12 and 40 feet are on the same position but on different figures. So I'm going to look at those ratios, 12 over 40 simplified to 3/10. I'm also going to look at 24 over 80 because those are corresponding side lengths. That also equal to 3/10. And I'm also going to look at 18 over 60, which also simplified to 3/10. So the ratios of these corresponding sides are equal. So we can now confirm that these two rectangular prisms are similar shapes. So we can say, yes, the figures are similar. Okay. Now, the next question says, if so, state the scale factor. So the scale factor is a number that enlarges or reduces a figure. So in this case, if I was to enlarge this smaller rectangular prism, which had a length of 12 feet, to enlarge it to a length of 40 feet, I would be using a number to multiply by 12 to get to 40. So that's our scale factor. In this case, we're enlarging the figure. Scale factor is also the reciprocal of the ratio. So the ratio of these corresponding side lengths were 3/10. That means that our scale factor would be 10 over 3 because it's the reciprocal of 3/10. So I'm going to put in parentheses reciprocal of ratio, just in case you want to take a couple notes off to the side. So that's our scale factor for problem number 1. And looking at number 2, we have two hexagonal prisms. We want to decide if these two shapes are similar, and if so, what would be the scale factor. So we're going to look at our corresponding side lengths and find out if those ratios are equal. So I am going to look at the ratio of 18 and 54 because those are the corresponding heights of our prism. So I'm going to look at 18 over 54, which reduces to 1/3. And I'm going to look at 6 over 21, which reduces to 2/7. So since 1/3 does not equal 2/7, then these two shapes are not similar. So no, 1/3 does not equal 2/7. The figures are not similar. Okay. Moving on to number 3, it says each pair of figures is similar. Use the information given to find the scale factor of the figure on the left to the figure on the right. All right, so we are going to be looking for the scale factor from the figure on the left to the figure on the right. So we're looking for a scale factor that will reduce the larger figure, the rectangular pyramid, to a smaller rectangular pyramid. And what's given right now are not the side lengths. We're given the volume. So we have to work backwards and undo our volume to get the scale side length. So right now we can look at the ratio of our volume scale. So we're going to look at 10,240 divided by 20,000. Okay. That volume scale is going to reduce to 64 over 125. Okay, so that would be the volume scale. But we want to find the scale factor of the figure from the left to the right. So we know that volume is in cubic units. So this number right here, this third power right here means cubic units. So volume is always in cubic units. So in order to undo something that's being cubed or taken to the third power, we're going to do something that's new for you today. We're going to take the cubed root. So that's how we're going to find the scale factor of the side lengths. So a cubed root is kind of like a square root, which you might have done in 6th grade. But a cubed root, we're looking for a number that is multiplied by itself 3 times. That will get us to the number 64 and 125. So our scale will be found by taking the cubed root, and in order to show that you're taking the cubed root of something, we're going to write the number 3 outside of our square root symbol. So we are going to find the cubed root of 64 and the cubed root of 125. So let me write both of my cubed root functions. I have one on the numerator, one on the denominator. So I'm going to think of a number that when multiplied by itself 3 times will get me to 64. So you can just start with 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4. That didn't take too long. So now 4 times 4 times 4 will get me to 64. So because there are 3 of the same whole real number underneath our third root, I know that the cubed root of 64 is 4. I'm going to do the same thing with 125. So the next number after 4 is 5 times 5 times 5. That didn't take too long to figure that one out. So sometimes if you don't have a scientific calculator, you can use guess and check. But if you do have a scientific calculator, there is a third root function on your calculators that you can use instead of having to do guess and check. But for us, for right now, we're just going to use guess and check. But it doesn't take that long. These are small enough numbers where we can do that. So a number like 5 times itself 3 times would get us to 125. So the cubed root of 125 is 5. So our answer for our scale factor for the side lengths, this is not for the volume, this is for the side lengths because we undid the cubic roots, we got 4/5 for our scale factor. All right, so let's take a look at number 4. We are given 2 cylinders that are similar, and they're given the surface area of the 2 cylinders. So if we're going to find the surface area scale, let's look at our numbers here. We have 175 pi. Let's divide that by 7 pi. So for our surface area scale, we are going to get 25. Okay, so since surface area is in square units, okay, we are going to undo that to find the surface area of the scale of the surface area of the side lengths by taking the square root. So in order to find the surface area scale, we just divided our 2 numbers there, but for the scale of our side lengths, we are going to take the square root of that number 25. So as you notice over here, I did put the number 3 outside of my root function, but when we do square roots, it's implied. If you'd like to put the number 2 out front, you can, but it is implied that we're doing the square root. So if you just see 2 numbers underneath the square root symbol, like this, 5 times 5 is 25, then we're assuming that we're taking the square root. You don't have to put the number 2 out front like we did over here with the 3. So again, we're finding 2 of the same numbers, real whole numbers that when multiplied together give me 25. It's called a perfect square. That number would be 5. So our scale of our side lengths would be 5. All right, moving on to number 5. It says that each pair of figures is similar. Find the scale factor of the figure on the left to the figure on the right. Then find the scale factor of the surface areas and the scale factor of the volumes. Leave answers in simplified fraction form. Okay, great. So I am going to look at the ratios of the corresponding side lengths. So I'm going to look at the 42 and the 24. Okay, so let's look at 24 divided by 42. We're going to simplify that and get 4/7. Okay, so the scale factor would be 4/7. I'm going to leave it as a fraction. It's so much easier to work with fractions than decimals, especially if they're not nice decimals. So the surface area scale factor. So remember, the surface area is in square units. So I'm going to take my scale factor and I'm going to square it. Okay, so when we square something, we are multiplying 4 times 4 and 7 times 7. So 4 times 4 is 16 and 7 times 7 is 49. And I'm going to leave my answer as 16 over 49. So for volume is cubic units. I'm going to take my scale factor, 4/7, and I'm going to cube it. So 4 times 4 times 4 is 64. And 7 times 7 times 7 is 343. And I'm going to leave my answer in fraction form. All right, next problem says the scale factor between two similar figures is given. The surface area and volume of the smaller figure are given. Find the surface area and volume of the larger figure. So we're given that the scale factor is 9/4 and the surface area is 256. So since surface area, to find the surface area of the larger figure, because we're going to enlarge it by a scale factor of 9/4, for surface area, remember that it's our scale factor squared. So we need to square 9/4 and multiply it by 256. So we have 9 to the second power, which is 81. 4 to the second power is 16, and we're going to multiply that by 256. Which gets us to 1,296. So this would be our answer for the surface area of the larger figure. We have 1,296 kilometers squared. Okay, so now we're given the volume is 1,536. So volume, again, for the scale factor, we need to cube it. So we are going to do 9/4 to the third power, and we're going to multiply it by 1,536. So we have 9 times 9 times 9, which is 729. 4 times 4 times 4 is 64. And then we're going to multiply that by 1,536. It's going to be a very large number, but on a calculator, 729 times 1,536, all divided by 64, is actually a really nice number. It came out to be 17,496 kilometers cubed. So that would go right here in this spot in the blank line, 17,496 kilometers cubed. Okay, so we are done with our first page. So we're going to go to our second page of our lesson. So pause the video if you need to go back and look at any of the work that I've done. Otherwise, we are moving on to our next page of our lesson. So the next page says that a tissue company uses tissue boxes that are rectangular prisms. The boxes have dimensions 10 inches long, 6 inches high, and 4 inches deep. The managers of the company want a new size for the tissue boxes. They have 3 requirements. The new boxes have to be rectangular prisms, use less cardboard than the original boxes. So let's go ahead and underline some of this stuff. So they have to be the same shapes, rectangular prisms. They have to use less cardboard than the original boxes, and they have to hold the same or greater volume of tissue as the original. The company proposes a new tissue box with dimensions 12, 4, and 5 inches deep. Does this new box fit the requirements? And we're going to explain. And the original dimensions were 10, 6, and 4. So let's look at the volume of the original, and then we'll look at the volume of the new box and see if that has a same or greater volume and if that satisfies one of the requirements. Then we'll look at the surface area of the old tissue box versus the new tissue box surface area and see if it uses less cardboard to meet that requirement. Okay, so first thing we can do is look at the volume of the old rectangular prism, which was 10 by 6 by 4. So that's 240 inches cubed. And we can also look at the volume of the new box, which is 12 by 4 by 5, which is also 240 inches cubed. So far it does satisfy that requirement right there. They do have the same or greater volume. They have the same volume. So now we have to look at the surface area to make sure it matches that requirement. So let's look at the surface area of the old dimensions. So surface area, since we're using rectangular prisms, we want to make sure that we use every combination of all three of our numbers. And we times by 2 because we're talking about prisms. So we have 2 combinations of 10 and 6. We have 2 combinations of 10 and 4. And we have 2 combinations of 4 and 6. Okay, so we're going to multiply all of these together and add them up. So we have 120 plus 80 plus 48. So all of that added together will give us 248 inches squared. So that's the surface area of our old rectangular prism, and the surface area of our new rectangular prism. We have to do combinations of all three of our new numbers. So we need 2 times 12 and 4 plus 2 and 12 and 5 plus 2 and 4 and 5. All right, so we have 96 plus 120 plus 40, and that'll get us 256 inches squared. So it looks like it doesn't match the requirements because we're using more surface area for the new box than the original old one. So we're going to answer the question and say no, the new box does not or doesn't fit the requirements. And we could say that 256 inches squared is greater than 248 inches squared. Sorry, I'm kind of running out of room right there. Okay. It says for part B, give a possible set of dimensions for a new box. Explain why your box meets the requirements. So go ahead and pause your video, and I want you to think of 3 dimensions that would satisfy the requirements that it either has the same or greater volume, and the surface area has to be less cardboard than the original box. Okay, so hopefully you came up with some numbers. Some of the numbers that I was thinking of, or maybe using the fact that I can get 3 other numbers to equal 240. I was thinking of choosing maybe for my new volume to be dimensions of 6, 8, and 5. So that would also give me a volume that's equal to 240 inches cubed. So I just need to check if this new surface area is going to use less cardboard than the original box of 248 inches squared. So let's go through our combinations of all 3 of these dimensions. We have 2 combinations of the 6 and 8, 2 combinations of the 6 and 5, and 2 combinations of the 8 and 5. So we have 96 plus 60 plus 80. So that would give me 236 inches squared, which is going to satisfy the conditions that it has to be less than 248 inches squared. So let's give our explanation. We're going to say yes, this new box meets the requirements. And we can say that 236 inches squared is less than 248 inches squared. Okay, so for problem number 8, it says for each of the following problems, find the necessary measurements to answer all the questions. It says a cube with side lengths of 8 centimeters is enlarged, so its side lengths are now 24 centimeters. Part A, by what scale factor did the side lengths increase? So we're looking for scale factor and show your work to justify your answer. So for scale factor, we're going to look at our given side lengths. We have a length of 24 centimeters and we have a length of 8 centimeters. If we were to look at that In simplest form, we would get a scale factor of 3. So that was our work, and our scale factor would be 3 for our side lengths. Then it says, by what scale factor did the surface area increase? The last time we were finding the lengths, now we're looking at the surface area scale factor. So show your work to justify your answer. So surface area scale factor is the square of our side length scale factor. So this was our scale of just our side lengths. Oh, I spelled that wrong. So our surface area scale would be 3 to the second power, which would be 9. All right, and the last one on this page, it says, by what scale factor did the volume increase? Show your work or justify your answer. So for our volume scale, we are going to take the cube of our length scale, which is 3 to the third power, and that would be 27. All right, so pause the video if you need to go back and look at anything on this page. Otherwise, we are going to go to our last page. Okay, so for problem number 9, it says a rectangular prism with side lengths of 5 yards, 10 yards, and 15 yards is reduced by a scale factor resulting in new sides of 1 yard, 2 yard, and 3 yards. What is the scale factor for the reduction? So we're looking at the lengths. So we're going to be reducing this. So we're going to reduce it by a scale factor of 1 over 5. By what scale factor did the surface area change? So this is the scale factor of the lengths. I'll spell it right this time. We're going to look for the surface area scale factor this time. And we're also going to look for the volume scale factor. Okay, so the surface area scale is our length scale squared. So we have 1 over 25, and our volume scale is our scale to the third power. So that would be 1 over 125. All right, what would be the new surface area and volume for the prism? So I'm going to go back up to my new dimensions up there, which were 1 by 2 and 3. So the surface area, I need combinations of all of those numbers. So I'm going to multiply 2 combinations of 1 and 2. I'm going to multiply 2 combinations of 2 and 3. And I'm going to multiply 2 combinations of 1 and 3. So I get 4 plus 12 plus 6, which is equal to 22 yards squared for my new surface area. And my new volume, I'm going to just multiply 1 and 2 and 3 together. Those are my dimensions, and that is 6 yards to the third power. All right, last one is problem number 10. It says a rectangular prism with side lengths 2, 3, and 5 millimeters is enlarged by some scale factor. The new volume of the prism is 240 millimeters to the third power. By what scale factor would the side lengths increased? Okay, so we are looking for the scale factor of the side lengths, and notice that they give us the volume is 240. They don't give us the surface area or that we're actually, I don't think we need to find the surface area until part C, but for the scale factor of the side lengths, we need to figure out the volume of the new figure. So the volume of the old figure was 2 times 3 times 5. Okay, so multiplying all of those together, we get 30 millimeters to the third power. Okay, so that would be the volume of the old. And since we're given that the volume of the new prism is 240, let's take a look at that volume scale. So we're going to divide 240 by 30. So that would be 8. So this would be our volume scale. And we're trying to find the scale of the side length. So remember, in order to undo the volume scale, which volume is in cubic units, we need to find the cube root. So to find the scale of the lengths, remember, we have to find the cubic root of this number 8. So I know that 2 times 2 times 2 is equal to 8. So as long as there are 3 of the same number multiplied by itself, we can take the cubic root of that function, which is 2. So the scale side length would be 2. So it says, what is the new length of each side? So since the original side lengths were 2 millimeters by 3 millimeters by 5 millimeters, I'm going to increase it by the scale factor of 2. So basically, I'm just going to multiply all of these dimensions by 2. And I'm going to get my new side lengths of 4 millimeters, 6 millimeters, and 10 millimeters. All right, last one. It says, what is the new surface area of the prism? So my surface area of my new prism would be to take the combinations 4, 6, and 10 and multiply them by 2. So every combination, so I'm going to start with 2, 4, and 6, 2, 6, and 10, and 2, 4, and 10. So I have 48 plus 120 plus 80. So all of those added together would get me a total of 248 millimeters to the second power. So that's our new surface area. All right, I hope you had a wonderful time doing the lesson together, and I will see you soon. Thanks, Math A Honors students. Have a wonderful day.